About section 6.8, pseudo-rigid body models for four-bar mechanisms. And four-bar mechanisms show up quite a bit just for ordinary mechanisms, and a lot of pseudo-rigid body models can turn into four-bar mechanisms, and they're pretty versatile. So it's nice to have a fairly solved version, and so we can use this idea of virtual work to get us a lot of information. And so in this section, gives several equations for how to handle the virtual work for a four-bar mechanism. And there's certain assumptions that go into it. We've got the standard sort of virtual work equation right there in 6.108. And you've got your forces and your moments, and then you've got your sources of potential energy, or TI. Those are just the springs. Okay, so now you can break down the force into an X and Y component, and so you got a F sub I. The sub I is just the link that it's acting on, and so this cap X sub I and cap Y sub I, that's just the X component of the force on the ith link, or so X2 would be the X component of force on the second link, and cap Y2 would be the Y component of the force on the second link. Anyway, so that's kind of nice to have that terminology. And so we consider all the possible things I could do on a four-bar. And this is not all-inclusive, but it's pretty good. And you can do most of the things you'd ever want to do with a four-bar using this system. Okay, and so this picture includes torsional springs at every pin joint. It also includes a force at some arbitrary location on every link, and then some sort of moment applied to every link. Okay, and so that covers most of what you could conceivably want to do to a four-bar. Now, ordinarily, you wouldn't have all these. In fact, you might only have one or two or maybe three of these at any one time. And so, but what's nice is if we derive the equations including all of these, you can just set a bunch of things equal to zero, and you know what the effects are going to be of each thing, and so you can just look at the ones that actually apply to the particular problem you have. Okay, and so the fact that in this section that Dr. Hallow derives the equations for a pretty general sort of circumstance means that most of the work is done in deriving the equations for a four-bar for about any circumstance, any four-bar circumstance you can think of. Okay, so a couple equations he gives you here. Gives you the equation for example, Z2. That's the point where the force on link 2 is applied, and dZ2 would just be the infinitesimal displacement of that. So when you think of that as the mechanism moves, it's going to move a little bit in that particular direction. Okay. You also have these the torques that act on it due to the torsional springs, and that are just going to be moments that are functions of the position angles of the links. Okay, and so you can write that the torque is just going to be the torsional spring value K times an angle expression that he writes as psi. And the different types of psi he's got all written out for you. And I talked a little bit about this in an earlier example. These are just all the possibilities for a four-bar. You can see that they have a pretty predictable format, in that they're just the moving angles, first off, involved. So psi 1, that's associated with the angle between link 1 and link 2. Since link 1 doesn't change, it disappears from this expression. The psi 2 and psi 3, okay, so psi 1 happens here, psi 2 happens here, psi 3 happens there, and psi 4 happens down at this corner. And so you notice that the angles that are associated with the ground links only have a simpler expression, and the ones that are associated with the moving pivots have a little bit more complicated expressions. Now, the other thing that's kind of interesting about this is, based on how these are used in the expressions, The potential energy for these things uses a psi squared term, or a psi times d psi. And what comes out of that is actually kind of interesting, is that you don't actually have to memorize that, he's got it as theta 2 minus theta 2 naught minus theta 3 minus theta 3 naught. As long as you've got all those terms in place where it's the difference between theta 2 and its original angle minus the difference between theta 3 and its original angle, you can flop the orders of those. So you could have, say, you could have this expression subtract and then subtract that expression from it, and the math works out the same way. So, and that's because potential energy is a square of that difference. And so as you work through that, it really doesn't matter that you get the which term subtracts from which, as long as you've got this term in parentheses subtracting another term in parentheses, it's all good. All right. Though once you've picked that form, this form comes along with it. Okay. So up here, the minus sign goes with the theta 3. The minus sign then has to go with the minus delta theta 3. Okay. Now, what happens when we line all these up and do our virtual work expressions and plug everything in? You'll have some terms that go with the change in angle theta 2, some terms that go with the change in angle theta 3, and some terms that go with the change in angle theta 4. And you can gather up all those terms, and you've got a list here of all the possible ones that you could have. Okay, and so in some sense, all the hard stuff is right there in those expressions for A, B, and C. And so you can look at those, and depending on what you actually have in your problem, most of those are going to go to 0. So you're not going to usually have such a complicated expression. And so you can simplify things quite a bit using these A, B, and C expressions. Now, what then happens is typically you'll pick, for example, if we choose theta 2 as a generalized coordinate, our virtual work expression goes like this, and virtual work is equal to 0 at equilibrium. And so we'll have an expression that looks like this, where we'll have A plus B, then a kinematic coefficient, plus C times a kinematic coefficient equals 0. And that will be our equilibrium expression. Okay? And then we have those kinematic coefficients that we've learned how to derive. And so in some sense, we don't have to have theta 2 as a generalized coordinate. We can have these other ones as generalized coordinates, and that'll give us possibly other expressions. Okay, so, and we can get whatever kinematic coefficient we need. So the kinematic coefficients, if I have, say, I'm interested in d theta 2, d theta 3, that's just going to be the inverse of d theta 3, d theta 2. Okay, and so they're easy enough to take the reciprocal of to get to change what the independent variable is. Okay, so we have here, these are basically our expressions of equilibrium, kind of in a generalized form, this A plus B H32 plus C H42 equals 0, and we've got these other ones. Now all these are equivalent, okay, so you can choose whatever independent variable, whatever generalized coordinate you want, and you will get equivalent information. So it's really a choice, and it's not a particularly constrained choice which one you pick in these sort of equations. Okay.